This presentation provides an overview of big data and databases, focusing on the technologies and architectures used for handling massive datasets. Big data refers to datasets that are too large or complex for traditional data processing applications to handle adequately. It is characterized by the 5 Vs: volume, velocity, variety, veracity, and value. On the right, you will find a comparison between traditional data and big data. Traditional data typically involves gigabytes or terabytes, structured formats, batch processing, centralized architecture, and relational database management system solutions. Big data, on the other hand, often involves petabytes or exabytes, structured, semi-structured, and unstructured data, real-time processing, distributed architecture, and NoSQL and specialized solutions. Let's delve into the 5 Vs of big data. The first V is volume, which refers to the quantity of data generated and stored. For example, Facebook processes over 500 terabytes of data daily. The second V is velocity, representing the speed at which data is generated, collected, and processed. An example of this includes Internet of Things sensors generating real-time data streams. The third V is variety, which encompasses the different types and formats of data, including structured, semi-structured, and unstructured data such as text, images, videos, sensor data, and logs. The fourth V is veracity, which is the quality, accuracy, and trustworthiness of data. Ensuring data integrity in social media analytics is an example of addressing veracity. Lastly, value, the ability to derive meaningful insights and business value from data, such as predictive analytics for business decisions, constitutes the fifth V. Big data storage technologies include distributed file systems, which manage storage across multiple machines, providing high-throughput access to data. Examples include the Hadoop Distributed File System, HDFS, the Google File System, GFS, and the Ceph File System. NoSQL databases are non-relational databases designed for distributed data stores with flexible schemas for modern applications. These include document stores like MongoDB and CouchDB, column family stores like Cassandra and HBase, and key-value stores like Redis and DynamoDB. Data warehouses are centralized repositories optimized for analytics and reporting on large volumes of structured data, such as Amazon Redshift, Google BigQuery, and Snowflake. Finally, data lakes are storage repositories that hold vast amounts of raw data in its native format until needed. Examples include Amazon Simple Storage Service or S3, Azure Data Lake Storage, and Google Cloud Storage. NoSQL databases come in various types, each suited for different use cases. Document stores store data as documents, such as JSON, BSON, or XML, with flexible schemas. They are ideal for content management and user profiles. An example of a JSON document is provided showing fields like ID, name, email, and age. Key-value stores use a simple data model, storing values indexed by keys, and are excellent for caching, session management, and high-speed lookups. An example using Redis commands is shown. Column family stores store data in column families, optimized for queries over large datasets with high write throughput. An example using Cassandra Query Language, or CQL, to create a users table is presented. Graph databases store data in nodes and edges representing relationships, making them ideal for connected data like social networks and recommendations. An example using Neo4j Cipher to create person nodes and relationships is given. The Hadoop Ecosystem is an open-source framework designed for distributed storage and processing of large datasets across clusters of computers. Key components include HDFS, which is a distributed file system for storing data, and MapReduce, a programming model for parallel processing. Other components are Hive, a data warehouse for SQL-like queries, Pig, which is a high-level scripting tool for data transformations, HBase, a NoSQL database for random, real-time access, Spark, a fast, in-memory data processing engine, Kafka, used for distributed streaming, and Zookeeper for maintaining configuration information. MapReduce is a programming model for processing and generating large datasets with a parallel, distributed algorithm on a cluster. Its key characteristics include a divide-and-conquer approach, high scalability across hundreds of servers, fault-tolerant processing, processing data where it's stored, and handling structured and unstructured data. The MapReduce process involves several phases. First, input data is divided into blocks. Then, the map phase applies a function to each block, generating key-value pairs. The shuffle phase groups the data by key. Next, the reduce phase processes the group data to produce a final result. Finally, the output phase stores the results. An example of a word count implementation is provided. Several big data processing frameworks are available, each with unique features and use cases. Apache Spark is a unified analytics engine for large-scale data processing within memory computation, which can be up to 100 times faster than Hadoop MapReduce. Spark supports batch, streaming, machine learning, and graph processing, with APIs in Scala, Java, Python, and R. Its use case includes real-time analytics and machine learning pipelines. Apache Flink is a stream processing framework with precise control over time and state. It offers true streaming, not microbatching, with exactly once semantics and event time processing with watermarks, making it suitable for complex event processing and anomaly detection. Apache Storm is a distributed real-time computation system for processing data streams. It provides low-latency processing, at least once processing guarantee, and horizontal scalability, making it ideal for real-time analytics and continuous computation. Apache Kafka is a distributed event streaming platform for high-throughput, fault-tolerant pipelines, offering publish-subscribe messaging, durable message storage, and Kafka streams for stream processing, suitable for log aggregation, messaging, and activity tracking. Data warehouses and data lakes serve different purposes in data storage and analytics. Data warehouses store processed, structured data optimized for SQL queries, using a schema-on-write approach where data is structured before loading. This can be expensive for large volumes of data and less agile due to the difficulty of schema changes. They are primarily used by business and data analysts for reporting, business intelligence, and structured analytics, with examples including Amazon Redshift, Google BigQuery, and Snowflake. Data lakes, on the other hand, store raw data in its native format, whether structured, semi-structured, or unstructured, using a schema-on-read approach where structure is applied when data is accessed. This is cost-effective for large volumes of data and highly agile, adapting to changes quickly. Data lakes are used by data scientists, data engineers, and analysts for machine learning, predictive analytics, and data discovery, with examples including Amazon Simple Storage Service or S3, Azure Data Lake Storage, and Google Cloud Storage. Big data presents several challenges. Data privacy and security require protecting sensitive information while maintaining utility for analytics. Data quality involves ensuring accuracy, completeness, and consistency across massive datasets. Performance and scalability necessitate maintaining speed and efficiency as data volumes grow exponentially. The skills gap highlights a shortage of professionals with expertise in big data technologies and analytics. Finally, regulatory compliance requires navigating complex and evolving data protection regulations like GDPR and CCPA. The future trends include AI-driven data management, automating data preparation, quality control, and governance using machine learning. Serverless data processing offers on-demand, auto-scaling compute resources without infrastructure management. Real-time analytics provides instant insights from streaming data for immediate decision-making. Edge computing processes data closer to where it's generated, reducing latency and bandwidth. Data mesh architecture promotes domain-oriented, decentralized data ownership and architecture. In conclusion, the future of big data is not just about handling volume, but creating intelligent systems that can derive meaningful insights while respecting privacy and ensuring security. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.